Okay, so good morning, guys. Let's start the meeting. First of all, let me share this screen. Okay, so in the last class, first of all, tell me, am I audible to all of you? Am I audible, Varun?
Yes, sir.
Okay, fine. So yes, in Monday's class, I was talking about the synthesis and different characterization techniques that we make use of for a catalyst. Okay, so there are several characteristic features of a catalyst. However, we mainly talked about the surface area pore size distribution and also the surface acidic properties. There are several reactions where you will you will understand that how acidic surface sites play a major role in such reactions. Like in petroleum refinery, when we talk about like catalytic cracking reaction, hydrocracking reaction, sometimes in reforming operations also, acidic surface sites play a major role. Okay, so that is why you need to remember what is acidic surface site. So in the last class, I already talked about it. Surface acidity can be determined by a method called temperature program desorption analysis. So in this analysis, what we use is we use ammonia as a TPD probe gas. Okay, so what we do, first of all, we carry out the adsorption of ammonia onto the surface of a catalyst, and after that we increase the temperature from room temperature to a certain temperature. Let's assume that certain temperature is around 950 or even 1000 degrees Celsius. So at that temperature, what happens is desorption of ammonia is being carried out, and this is detected by a or recorded by a TCD detector. Okay, so TCD detector will detect some signals, and those signals will give us the amount of acidic surface sites this material or this catalyst is having. Okay, so means on Monday's class, I already talked about these things. So TCD signal in millivolt, this is plotted along the y-axis, and along x-axis we have got the temperature. So temperature increases from room temperature to a certain temperature. So what you will find is, if you carry out this reaction and during the desorption, and if you record the signal during the desorption operation, you will find three different peaks at three different temperature zones. Okay, so that means you can see desorption of ammonia at low temperature zone. Similarly, desorption of ammonia at intermediate temperature zone, and finally desorption of ammonia at high temperature zone. Okay, so at each temperature zone, we have got desorption of ammonia. So the ammonia desorption at low temperature can be attributed to the strong acidic surface sites, since strong acidic surface sites respond at a very low temperature. From our basic understanding, we know this. Okay, so this peak corresponds to the strong acidic surface site. That means desorption of ammonia is taking place at a very low temperature. So this is due to the strong acidic surface sites present in the surface of a catalyst. Okay, so this is the intermediate temperature zone. So in intermediate temperature zone, we have got intermediate acidic surface sites. And finally, at high temperature, we have got low acidic surface sites. That means this site doesn't have that much acidic property. So here the acidic property is the maximum. Here intermediate acidic property you can see. And finally, at very high temperature, we have got minimal acidic property left in the material, or in the catalyst rather. Okay, similarly, in some reactions, basic surface sites also play a major role. Okay, so in such case, all the reaction conditions and everything will remain the same as before. However, instead of ammonia, we will be using carbon dioxide as a TPD probe gas. Carbon dioxide is acidic in nature. Ammonia is basic, everybody knows it. So instead of ammonia, what we will do is, first of all, we will take a U tube. This is made up of quartz. Okay, so inside this, I have got around 100 milligram of the catalyst material, and we are allowing carbon dioxide to pass through this. So as a result, what will happen is carbon dioxide will get absorbed onto the surface of the catalyst. So this is the adsorption, and this adsorption operation is conducted at room temperature. Let's assume the room temperature is around 30 degrees Celsius. So we perform this at room temperature. Next, what we'll do is, and also remember this thing already I mentioned about this. So this is mounted, okay, inside a furnace operated under PID mode. PID means proportional integral derivative mode, and we increase the temperature from room temperature to a certain temperature at a temperature ramp of around 10 degree per minute. You can also carry out the same reaction at a temperature ramp of 5 degree per minute, but it will take more time. Okay, so if you don't have too much time to spend on this, so we can increase the temperature ramp to 10 degree per minute. This is the maximum temperature ramp we can use. If we use means above 10 degree per minute, it is not desirable at all. So 10 degree per minute is the optimum temperature ramp that one should use. You can also carry out the same reaction with 5 degree per minute temperature ramp. However, 10 degree per minute temperature ramp is basically the optimized one. Okay, so this is mounted inside a furnace, and the furnace is operated under PID mode. And by PID mode, what we are doing is we are increasing the temperature, and the temperature ramp is around 10 degree per minute. So as a result, what will happen is we'll get, and also we will be recording, and this is the outlet of this is connected to a temperature thermal conductivity detector. So this detector detects the amount of ammonia for acidic surface sites and amount of carbon dioxide for basic surface sites. Okay, so this unit would be micromole per gram. Always remember this. So we'll quantify the amount of ammonia dissolved or amount of carbon dioxide dissolved in terms of micromole per gram. So per gram of catalyst. So 1 gram of catalyst is a basis. So per gram has to be mentioned, not only the micromole. Okay, so what will happen is, similarly for carbon dioxide also, we'll get 3 different peaks at 3 different temperature zones. So these peaks will correspond to the desorption of carbon dioxide. Okay, so suppose we don't have, our material doesn't have any acidic or basic surface sites, then a flat signal like this will obtain. Okay, so there will be no TCD signal as such, so it will be a flat line. This would be parallel to the temperature axis. Okay, suppose we don't have any acidic or basic surface sites in our material, so the TCD signal will look like this. However, if our material has got basic property and we are allowing CO2 as a probe gas to enter through to pass through the catalyst particles, so we'll have this kind of peaks. So the peak at low temperature zone corresponds to the desorption of carbon dioxide. Similarly, at intermediate temperature also we have got a peak that also can be attributed to the desorption of carbon dioxide. Similarly, at high temperature, we can also have a desorption of carbon dioxide. So this is basically due to the strong basic surface sites. This is due to the not weak, intermediate basic surface sites, and finally this one is correspond or attributed to the strong or not strong, weak basic surface sites. So this is due to the strong basic surface sites, this is intermediate basic surface sites, and this is due to the weaker basic surface sites. So we have got 3 different peaks at 3 different temperature region. Okay, an amount of carbon dioxide dissolved or amount of ammonia dissolved can easily be calculated using the signal. Okay, so an area under the curve, we make use of area under the curve in order to calculate this, and this is calculated in terms of micromole per gram. So here we have taken a basis of 1 gram of catalyst. Okay, so these are the 2 important surface properties of a catalyst. And also remember one thing, surface area I already talked about by a method called BET surface area and pore size distribution analysis at a temperature of around 77.35 Kelvin. So 77.35 Kelvin is basically the liquid nitrogen temperature. Okay, so here we obtain the surface area, but remember one thing, the surface area means if the material has got huge surface area, it doesn't mean that all the surface area is available or for the reaction to take part. Okay, so out of 100% surface area, we have got very minimal surface area. Let's assume 5 to 10% of surface area that is considered to be the active surface area. So this active surface area is responsible for the catalytic reaction. However, remaining 90 to 95% surface area is considered to be the inactive surface area. So inactive surface area doesn't take part in a catalytic reaction. Okay, So for a catalytic reaction, we need to have active surface area and also acidic or basic surface sites. That depends on the type of reaction we are carrying out. But active surface site is the common for all type of catalytic reaction. Okay, so these are the two essential characteristic features one catalyst should possess. So now coming to the concept of catalyst deactivation. Can anybody tell me what is catalyst deactivation? Hopefully all of you have studied this thing in chemical reaction engineering by now. Varun, what is catalyst deactivation?
I think loss of its capability to act like how it used to before.
Yeah, this is correct, but scientifically I wanted to learn something more from you. Okay, so let's assume I have got a catalyst. So this is the pictorial representation of a catalyst, but no catalyst looks like this. Okay, if you put certain catalysts under the microscope, you will find different types of morphology. But for the sake of simplicity, I'm showing you a catalyst like this. So this is the rectangular box is basically the support. So here, always remember, I'm talking about a supported catalyst. Okay, so here I have got a support like this, and on the support side, I have got dispersion of active metals. Okay, so active metals like these dots are basically the active metal part, and support can be represented as a rectangular chamber or rectangular box rather. Okay, so remember this. So now if our material has got low surface area or the support material has got low surface area, then what will happen? This scenario will happen. Can anybody tell me why is it so? Okay, so these are basically the active metal parts. If our material has got low surface area or the support material rather, remember that I told you, right, while teaching you the synthesis of a supported catalyst, I told you that first of all I need to have a support. The support should possess medium to high surface area. It shouldn't possess low surface area. Why is it so? Since on the surface of a support, we are going to incorporate the active metals by a method called impregnation method. There are several other methods as well by which we can also incorporate the active metal part on the surface of a support. But however, for the time being, let's assume we are just using impregnation method to deposit the active metal part on the surface of a support material. So if the support material has got low surface area, so then this type of scenario will happen. Okay, why is it so? Since our material has got low surface area and we are allowing the impregnation method in order to incorporate the active metals, so active metals will come in contact with each other and there will be the non-uniform and non-homogeneous distribution of active metals. Okay, so as a result, what will happen is the catalytic activity will drop down. Why is it so? Any idea? If the active metals are uniformly and homogeneously distributed, so this should be the ideal situation. Okay, and here we are considering that the support material has got either medium or high surface area. If the material has got low surface area, so we have got less space available for the active metals to get incorporated on the surface. So as a result, what will happen is they will come in contact with each other and there will be a dense deposition of active metals on the support material. So if we have got distribution of active metals like this, then what will happen is all the active surface sites of these metals are not available for the catalytic reaction. Let's assume I have got a scenario like this. I'm allowing one gas molecule, not a gas molecule, it's a flow process, let's assume. Okay, so we are allowing, let's assume carbon dioxide. So carbon dioxide will come in contact with these particles and they won't follow a straight line, right? It will follow a tortuous, but I'll talk about it in a short while from now. So for the time being, remember that we have got distribution of active metals like this. So all the surface sites, active surface sites rather, are not available since we have got dense like deposition of the active metals here like this. But the ideal situation should be like this. If the ideal situation is like this, then carbon dioxide molecule will get enough space to interact with all the active surface sites if we consider only one single active metal part, right? So means there won't be any diffusion limitation. But however, in this case, we have got diffusion limitations, right? We don't have much space for the carbon dioxide molecule to come in contact with each and every active metals here, right? So as a result, what will happen is the catalytic activity will decrease. Okay, so this is not the ideal situation. So that's why we won't use any catalyst material, or rather a support material which possesses low surface area. Okay, surface area means surface area in terms of meter square per gram. Okay, so this should be the ideal situation, since there we don't have any diffusion limitation. But here in this case, we have got diffusion limitation, and as a result, what will happen is not all the active surface sites are available for the carbon dioxide molecule to interact. As a result, what will happen? The catalytic activity will of this catalyst will decrease. Okay, so whatever catalytic reactions I'll be talking about throughout this CPT course, all the catalytic reactions are either performed in a fixed bed or in a fluidized bed. But in the petroleum refineries, you will understand that most of the catalytic reactions are performed, most of them means over 90% catalytic reactions are performed in the fixed bed. Okay, so if this is a pictorial representation of a fixed bed reactor. So we have got a reactor, inside this I have got a bed. Okay, so in case of petroleum refinery, I'll teach you that we don't use a bed made up of powder. Instead of using a bed made up of powder, we'll use pellets inside this bed. That means we have got a bed, so we have got layers of pellets. Pellets will be made up of this catalyst only. So catalysts are basically in the powder form, right? So if the catalyst is in the powder form and we are incorporating those powders inside this bed, then what would be the scenario? Can anybody tell me? Let me repeat again. I have got a fixed bed like this. So this is a fixed bed pictorial representation or schematic representation of a fixed bed reactor. So inside this fixed bed, I have got particles there. Okay, so catalyst particles I'll have to put, and I will allow some gas molecule to penetrate through this. Okay, the moment it will come in contact with these particles, reaction will take place. Okay, and from the outlet we'll get the desired product, undesired product plus unconverted reactants. So through this, reactants are being incorporated, and by this we are means taking out the product plus unconverted reactants. Okay, so now consider we have got a fixed bed like this, and inside this fixed bed we have got solid particles. Solid particles means catalyst particles in a powder form. Then what will happen? Varun, what will happen?
I'm not sure.
Not sure. First of all, let's talk about the particles. Okay, that means a powder bed made up of catalyst powder. Then what will happen is, ideal situation should be like this, right? So this is the inlet. So from inlet, we are allowing hydrocarbon. Let's assume we are having hydrocarbon gas here. So we are allowing hydrocarbon gas, and it should penetrate through the bed like this. But this is not the actual situation. Whenever we are allowing any hydrocarbon or any other gas to penetrate through a bed made up of powder, then it follows the tortuous path like this. It doesn't go like this. Okay. So this should be the one can think that this should be the ideal situation, but this is not the ideal situation at all. In real life situation, we'll find like this. So it follows the tortuous path like this. And so this is the inlet and this is the outlet. So gas molecule will follow a tortuous path throughout the bed, and it will go out like this. As a result, what will happen is there will be unutilization of bed. So this part of the bed will remain unaffected, or this part of the bed won't come in contact with the gas molecules. You can see it over here, right? So the gas molecules are following the tortuous path like this. Here also we have got a tortuous path. This part of the bed is unaffected. Similarly, this part of the bed, even this part, that part, and this part of the bed is also unaffected, which we don't want. We want to make use of the entire part of the bed in order to improve the overall productivity, right? That is why we don't use a powder in a bed. Instead of using a powder, what we do is with that powder we make pellets of roughly 3 diameter. Okay, and then we introduce those pellets inside this bed and we carry out the reaction. Okay, let me repeat it again. Let's assume I have got a fixed bed reactor like this. So this is the schematic representation of a fixed bed reactor. So we have got two situations. In one situation, we have got like a bed, fixed bed. Inside this fixed bed, we have got powdery material. Powdery material means catalyst in the powder form. Okay, so this is the inlet, this is the gas outlet. So from inlet, we are allowing some hydrocarbon gas to pass through this bed. And through outlet, we are collecting the product, that means desired product, plus undesired product, if any, plus unconverted reactant. If we don't have 100% conversion, then we will have some unconverted reactant left in the outlet part, right? So this is our inlet, this is our outlet. So let's assume I have got a fixed bed like this with a powdery material and I am allowing the hydrocarbon gas to pass through this. So it should follow a path like this. From our normal understanding, we can think of this. Like this will follow this kind of path. Means all the part of the bed will be utilized. However, in real life situation, it doesn't happen so. In real life situation, what happens? We're allowing any hydrocarbon gas to pass through it. The moment it comes in contact with bed, it follows a tortuous path like this. Here we have got tortuous path. Again, here also we have got one tortuous path. Here I have shown another tortuous path. So what will happen is most of the part of the bed will remain unaffected, which we don't want. If we have made a bed like this, we want every single part of the bed will take part in that catalytic reaction. Otherwise, there is no point in carrying out such reaction. At the end, what will happen is we will have loss of productivity, which we don't want. Okay. So everything costs money. So whenever we carry out any reaction, that also costs huge amount of money. No industry can run in loss, right? However, in most of the Indian industries, we are running in loss. So that's the real life situation. But in ideal situation, this should be like this. Means we want the each and every part of the bed to be utilized. Okay, but in real life situation, this thing happens. So it follows a tortuous path. If it is following the tortuous path, then most of the part of the bed, like this part, this part, this part, even that part, that part, that part, and this entire region will remain unaffected. That means this part of the bed won't come in contact with the reactant gas molecules. As a result, what will happen is we have got more unconverted reactants plus some desired product. However, the overall yield or productivity, maybe it's around 60%, 50%, 70%. But our aim would be to get around 100% conversion, right? So we'll have around 40%, 30%, 50% loss in the productivity, which we don't afford, which we can't afford, right? So that is why what generally people do is, or in industry, what people do is, let's assume we have got the catalyst. So instead of putting the powder form, what we do, we make a pellet out of that catalyst particles. Okay, so how to make it? By a hydraulic press or a pelletizer machine. By this, we can make pellets. Roughly, pellet diameter is around 3 for a petroleum refinery based process. Okay, so in petroleum refinery, generally we use pellets with 3 diameter. So inside this bed, we'll have several layers of these pellets. If we have got more pellets here, so the overall effective surface area will increase. As a result, there will be more interaction between the reactant gas molecules and the pellets. This will eventually lead to the formation of desired product. Let's assume we are getting around 95 or even 99% desired, 99% conversion of the desired product. So in order to improve the overall productivity, instead of using a particle or a powder, we will be using pellets. So if we have got pellets, so with pellets we can form a bed like this. We can have several layers of pellets inside a bed, and if we have got a pellet, then the overall surface area of the catalyst particle will increase or will be enhanced, and as a result or consequently, more reactant gas molecules will come in contact with the pellet, and as a result, the overall productivity of the desired product will increase. Okay, so this was the conception. Okay, so this has to be clear. So instead of using a powder, in most of the industries, if we are using a fixed bed reactor, so we will be using pellet instead of powders in order to improve the overall productivity. Otherwise, what will happen is, if we have got powder instead of pellets, then overall productivity will drop down because of the simply underutilization of the bed. Or this is sometimes called as maldistribution of flow. Okay, maldistribution of flow. That means we have got gas molecules. This is following the tortuous path. So this is called the maldistribution of flow. In industry, we don't want this. In order to avoid that, we are making pellets and we are dispersing these pellets in a bed. Maybe we can have several layers like this made up of pellets, and with these pellets we carry out the reaction, and as a result we get higher productivity. Okay. So now coming to the catalyst deactivation part. So catalyst deactivation can be of three types. Okay, there are three different classifications. So first one is basically the called the coking. Second one is sintering. Third one is poisoning. Okay, so these are very important things. If somebody wants to work in an industry, so they will encounter these problems. Coking problem generally people encounter when we are handling hydrocarbon feedstock. Okay, so suppose I'm handling a hydrocarbon feedstock. In a fixed bed reactor, I'm going to purge hydrocarbon. Then we can have the coking related issue. Sintering related issue we encounter when we carry out a reaction at a very high temperature for a prolonged period of time. Okay, I'll talk about all three one by one, but for the time being, remember, coking issue arises when we have got feedstock, which is hydrocarbon. Okay, so the hydrocarbon feedstock, we encounter coking related issue. Sintering related issues we encounter when we are carrying out any reaction at a very high temperature, okay, for a considerable period of time. I'll talk about what is coking, what is sintering, and what is poisoning. Poisoning we generally encounter when our feedstock is not pure. When we handle the impure feedstock, so this impure feedstock has to be pre-treated. Okay, unless we pre-treat, we'll always encounter this kind of poisoning effect. Poisoning effect means there will be irreversible chemosorption. By now, I think all of you know what is physisorption. Physisorption I have already covered in this class. Okay, chemosorption I haven't talked about. Probably in catalysis part of chemical reaction engineering, you have been taught, right, what is chemosorption. Chemosorption means chemical bond formation taking place. And in case of physisorption, we have got like weak van der Waals force of interaction. Okay, there could be some hydrogen bonding as well, and electrostatic interaction also plays a major role in physisorption process. But in case of chemisorption, there will be a definite bond formation taking place. Okay, so hopefully all of you remember this. So with this understanding, we'll move to the coking operation. So before coking, so what is poisoning? Poisoning means I have got handling a feedstock. So our main idea is I have got a feedstock. That feedstock will be passed through a reactor bed. Okay, and as a result, we are from the outlet, we will be collecting the desired or desired plus undesired product, if any. But in real life situation, if you are handling a feedstock that is impure, that means it contains sulfur, arsenic, okay, some other impurities also, sulfur, arsenic, chlorine containing impurities also sometimes we can have. Then what will happen is this will poison the catalyst. Okay, chlorine, sulfur, there are several other impurities as well. Arsenic also, lead also, right? So what they will do is they will make irreversible chemosorption. There will be a bond formation taking place between the poisoning particles and the catalyst. Catalyst means the active metal will form a bond with the poisoning particles like arsenic, sulfur, chlorine, etc., etc. So this is called the poison. Okay, so let's go one by one. First of all, let's talk about the coking. So can anybody tell me what is coking? Probably in first or in the second class, I have already mentioned what is coking. What is coking? Anyone? These things were covered, right, in the class? In petroleum, not petroleum refinery, in the catalytic chemical reaction engineering. What is coking? Here I have written deposition of amorphous carbon on the active surface sites of a catalyst. So how does this thing happen? Yes. Tell me.
Forms a layer over the catalyst. The carbon gets deposited over the
Right.
catalyst,
Right.
preventing contact by the reactants with the catalyst.
Right. So coking means we're handling one hydrocarbon feedstock. I have already talked about it. Okay. So we have got a hydrocarbon feedstock. This is our inlet. This is our outlet. Sometimes inlet is from the bottom and outlet is from the top also. Okay, we can find. But here let's assume the inlet is at the top. So here from inlet we are allowing CXHY. CXHY is the general representation of a hydrocarbon gas. Okay, so CXHY is being allowed to pass through this, and let's assume we are carrying out the reaction at a temperature of around 600 degrees Celsius. Okay, so from outlet we'll get hydrogen. Hydrogen is our desired product. Okay, hydrogen is a renewable gas, right? Renewable energy. So hydrogen has got huge importance in day-to-day life. So what is the major source of hydrogen? Hydrogen can be obtained by a cracking of a hydrocarbon. So cracking of hydrocarbon without a catalyst cannot be accomplished. So that is why what we do is in a fixed bed reactor, we have got a fixed bed that is made up of catalyst. So here I have incorporated the pellets of a catalyst, and we are allowing CXHY to come in contact with the pellets at a temperature of around 600 degrees Celsius. Okay. So at 600 degrees Celsius, what will happen is we will have carbon deposition plus hydrogen will be formed. So hydrogen is our main product. So this hydrogen will be stored somewhere. So as the time progresses, what we will see is the productivity of hydrogen. That means the yield of hydrogen will decrease with time. Why is it so? We are handling hydrocarbon feedstock. So at 600 degrees Celsius, the moment hydrocarbon gas is coming in contact with these particles, catalyst particles, what will happen is decomposition of CXHY is taking place. So decomposition of CXHY gives what? It produces carbon plus hydrogen. So this hydrogen escapes from the surface of this bed and it is being collected at the bottom. That means that from the outlet, we are collecting the hydrogen. So as the time progresses, we'll have coke deposition over the catalyst surface side, since carbon is being generated as a byproduct of this reaction, right? CXHY, so this will decompose to form carbon plus hydrogen. So with time, what will happen is we'll have more deposition of amorphous carbon. This amorphous carbon means this carbon is also filamentous in nature. Filaments means sometimes these are in spherical shape and sometimes they are in filamentous. Filamentous means in a tubular shape. Okay, so this would be the deposition of carbon. So carbon deposition will take place over the active catalyst surface side. So as a result, what will happen is we have got a carbon layer over the surface of the active metal part. Then what will happen is this carbon layer will prevent the penetration of CXHY. So there will be one diffusion barrier in between the hydrocarbon gas and the catalyst, isn't it? There will be one barrier, right? So what is the barrier here? The barrier is the carbon layer. So for CXHY, it will become next to impossible to penetrate through those carbon layers and come in contact with the active metal part. As a result, what will happen is after a certain period of time, we will find that the hydrocarbon conversion will drop down to 0. Okay, so this is called the coking effect. Coking effect means we are handling one hydrocarbon feedstock. So we are allowing hydrocarbon feedstock to come in contact with a fixed bed, okay, made up of catalyst. And we are allowing the reaction to be conducted at a temperature of around 600 degrees Celsius. So at 600 degrees Celsius, over the catalyst active surface sites of a catalyst, CXHY decomposes to form carbon plus hydrogen. Hydrogen is our major product that escapes from the surface, and we are collecting hydrogen at the bottom or at the outlet. And what happens to the carbon? This carbon gets deposited over the active surface site of the catalyst particles. So after a certain period of time, what will have is we'll have deposition of carbon layer. Okay, so as the time will progress, the deposition layer thickness will also increase. Try to visualize this. Okay, so what will happen is, let's assume I am carrying out the reaction for 1 hour. Up to 1 hour, I have got around 100% hydrogen yield. But as the time progresses, what will happen is the yield of hydrogen gets lower, lower, and lower. So why is it happening? Since with time we have got more deposition of carbon particles, since all the time CXHY coming in contact with the catalyst particle, it is decomposing into carbon and hydrogen. Okay, so with time what will happen is the coke layer, so that means the carbon layer will increase, the layer thickness will also increase. So if the layer thickness increases, then there will be a diffusion barrier. So what is the diffusion barrier here? So carbon thickness. As a result, what will happen is after a certain period of time, no CXHY will come in contact with the active catalyst surface site. And as a result, the hydrocarbon conversion will drop down to 0 with time, which we can't afford. So what we'll have to do is we'll have to immediately stop or terminate the reaction, and we'll have to take out, we'll allow to reactor to cool down to a room temperature. Okay. As soon as it reaches the room temperature, we'll have to take out the catalyst bed. Okay, take out the catalyst and we'll have to regenerate the catalyst. Until and unless we perform the regeneration operation, we cannot continue this reaction. Why we can't continue? Since with time we won't have any sort of hydrogen yield there. So hydrogen yield, once it reaches 0%, so it will follow the same path. So here I have given, means I have drawn one plot. Here I have along y-axis, I have shown the hydrocarbon conversion percentage, and this is the timeline. Okay, so this is time of stream. So initially it was around 100%. After a certain period of time, the hydrocarbon conversion decreases like this, and at one time will arise when the hydrocarbon conversion will drop down to 0, and it will follow like this. There will be no further increase in the hydrocarbon conversion. Okay, why is it so? If we take out one particle, one pellet from here, so this pellet will look like this. This means it has got carbon deposition. Okay, carbon deposition, and this would be the thickness. With time, the thickness of carbon deposition will increase, and this thickness will act as a diffusion barrier for CXHY. Okay, so we have got this carbon layer. So next target means when we have got deposition of carbon, then what we'll have to do is we'll have to immediately terminate this reaction. Okay, since there is no point of conducting this reaction when we have got around 0% hydrocarbon conversion. Okay, until unless we regenerate this bed, we cannot carry out the reaction. So our objective would be to get 100% hydrocarbon conversion, but here in real life situation, I ended up with only 0% hydrocarbon conversion. So we need to regenerate the bed. Regenerate the bed means we need to get rid of this carbon deposition here. So how to get rid of it? Any idea how to get rid of carbon deposition? Remember, we allowed the reactor bed to come down, means to cool down to room temperature, and we disconnected this setup and everything, and we took out the catalyst pellets out of this bed. Okay, and we'll have to perform the regeneration operation. So regeneration of this catalyst will be performed by heat treatment, and also we can do the steam activation. These are very important in the exam. I'll ask questions from here. Remember this. Okay, so heat treatment can be performed at low temperature as well as at high temperature also. So when we are conducting the heat treatment at low temperature, then we can use the oxygen environment or the air atmosphere. So in the air atmosphere at around 250 degrees Celsius temperature, 200 to 250 degrees Celsius, will allow these pellets to interact with oxygen or air. As a result, what will happen is this whatever carbon particles you have got deposited over the catalyst surface sites, they will be removed in the form of carbon monoxide plus carbon dioxide. But here we are assuming that we have got complete means removal of carbon. So our complete combustion of carbon. So here we'll think that we have got carbon dioxide formation, but this can easily be detected with the gas chromatography unit. If we take out certain amount of gas, okay, and you will purge it in the gas chromatography, you will find two different peaks at two different retention times. So one would be for carbon dioxide, another one would be for carbon monoxide. However, there will be very minimal amount of carbon monoxide also associated with this carbon dioxide, but let's assume we have got complete combustion. So we have got around 100% CO2 yield. Okay, forget about CO2. CO2, we don't need CO2, but CO2 has got some valuable applications as well. So this CO2 can be stored for different applications. But here we are concentrating on the regeneration of the catalyst. So I have got a pellet. That pellet, outer surface of the pellet is covered with the carbon particles, and we can carry out the heat treatment operation. The heat treatment can be carried out at two different temperatures, one at low temperature, another one at high temperature. So if we are adopting low temperature process, so low temperature process means we'll carry out the reaction at a temperature between 200 and 250 degrees Celsius in the presence of either oxygen or air. So whatever carbon particles we have got on the surface of a catalyst, that will be removed in the form of carbon dioxide. So now our catalyst is free of carbon. Okay, so this is one sort of heat treatment operation. The another type of heat treatment operation is at high temperature. Let's assume we are performing the heat treatment operation at high temperature. Then the high temperature means around 500 to or 550 degrees Celsius. Then instead of using oxygen atmosphere, we'll prefer to use nitrogen environment or an inert atmosphere. Okay, so in inert atmosphere also the final product would be the same. Here we will get carbon dioxide, but we need to adopt a very high temperature like around 500 to 550 degrees Celsius, since combustion of carbon in the inert atmosphere can be initiated at a high temperature. Like 500, we need at least 450 or 500 degrees Celsius to start the combustion process if we are carrying out the reaction in the presence of an inert atmosphere. Okay, but remember, if instead of inert atmosphere, we are using oxygen atmosphere, so at low temperature, we can initiate the combustion reaction. Okay, so this is called the heat treatment operation. So by heat treatment operation, we can get rid of the carbon particles deposited on the active surface sides of the catalyst. Okay, so the next one is the steam activation. So there are two different types of regeneration processes. One is like heat treatment, another one is called the steam activation. So in this case, what we'll do is, means we'll take a tubular reactor. Inside that tubular reactor, we have got catalyst particles. Catalyst particles, remember, these particles are in the pellet form. Okay, so catalyst pellets, and we'll allow steam, okay, to interact with those pellets at a temperature of around 900 degrees Celsius. So steam activation is performed at a very high temperature, like at around 900 degrees Celsius. So steam will interact with carbon particles, okay, at 900 degrees Celsius, and again carbon dioxide will be formed, and also some unconverted steam will come out of the reactor, and activation, following the activation operation, will end up with the catalyst in its pure form. Like there will be no sort of carbon particles deposited following the steam activation. But nowadays, heat treatment is more, means we are more familiar with the heat treatment operation, right? So if it is heat treatment, so we can carry out the reaction in the presence of an air atmosphere or in an inert atmosphere. But if we are adapting air atmosphere or oxygen atmosphere, the heat treatment can be performed at a very low temperature, not very low. 200 degrees Celsius is not very low temperature, but 200 degrees Celsius, 200 to 250 degrees Celsius, to remove carbon in the form of carbon dioxide. But remember, carbon dioxide has got some valuable applications as well. So this carbon dioxide we can transfer to the industry, where carbon dioxide made use of carbon dioxide as a feedstock in order to form different valuable products like methanol formation. Then also we can use carbon dioxide as a feedstock. Okay, so we have got two different regeneration methods. So one is called the heat treatment, another one is the steam activation. Steam activation is not that much in use. Let's assume we are handling huge amount of catalyst particles, since when in the lab we perform the reaction, we carry out the reaction with maybe max to max 1 gram of catalyst or 5 or 10 gram of catalyst like this, not beyond 100 gram of catalyst. But in the industry, we need huge amount of catalyst, right? Since they handle very huge amount of catalyst to increase the overall productivity. So in such case, heat treatment is the most favorable process than the steam activation. Okay, so they will use the heat treatment to get rid of the carbon particles in the form of carbon dioxide. Okay, so this is what the regeneration process is all about. So following regeneration, what we do is again we'll reinsert the catalyst pellets inside the beds, and further we'll carry out the reaction. And again, when we'll encounter the same coking issue, the same treatment will be following. Again, we'll recycle it. Means recycling would be performed several times. Okay, to get rid of the coke deposition or coking issue. So when we have got coking issue, then we have got no productivity as such. So in order to enhance the productivity, again we will further have to do the regeneration operation. After regeneration, again we will feed this. We'll have to feed these catalyst pellets inside this bed, and we'll further carry out the reaction. These reactions are continued in a continuous manner. These are not the batch processes, right? So continuously we want to feed the reactant for 1 or 2 years without any delay, without any problems or troubles. Okay, but when we're handling the hydrocarbon feedstock, then we always encounter this coking problem. So when we have got coking issue, then we'll have to go for the regeneration. That means we'll have to take out the catalyst particles from the bed. Okay, we'll have to disconnect everything, and it takes time. Okay, regeneration is also time-consuming process. Okay, but when you have got coking issue, we can do nothing but the regeneration of the catalyst if we want to use that catalyst again. Okay, so this was all about the regeneration of the catalyst. So is this clear to everyone? I don't know how many of you are attending this class, but is this clear?
Yes.
Yes. Okay. Oh, remember one thing, on 30th of March, I will conduct one small test. This will be online test. Okay. So all of you are coming back to the campus by 31st, is it so?
Yes, sir. That is the current guideline.
Okay. Since the final NSEM examination will be conducted in an offline manner. So yeah. Okay, so 30th or before 30th also I can do. Maybe some of you will be traveling on 30th, right? If I conduct this test on a one Saturday, would that be good for you?
So will April first week work? Because I think by then everyone would be on campus.
Yeah, but that test will be online, conducted online, okay?
Yes, sir.
And the final NSEM I will be conducting offline.
Yes, sir.
Okay.
Yes,
Okay,
sir.
so first week of April, then when will I conduct the NSEM exam? Since there is a guideline, and according to the guideline, between 7th and 19th of April, I'll have to conduct it. Okay, so
Yes,
this
sir.
is the deadline. 19th is the deadline. So after 19th, I can't conduct it. But if I conduct one test on say first week, okay, that will be good for you guys also. It will be a revision. So yeah, okay, no problem. I'll conduct the means test in the first week of April. No problem. Okay, so regeneration is done. So what is next? Next, I'll talk about sintering process. So tell me, what is sintering?
So that is melting of the catalyst due to high temperatures.
Melting of catalyst due to high temperature. How is it done? Only melting of catalyst. Sintering means only melting of catalyst, nothing else. So tell me, in order to avoid sintering, what should one do? In order to avoid sintering, what should one do? Sintering can be of two types. By now, I think that what is pores, what are the different types of pores on the surface of a catalyst. These things are clear to you, right? You know, right? There are three different types of pores. Like one is micropores, where the pore diameter is less than 2 nanometers. In case of mesopores, pore diameter range between 2 and 50 nanometers. And for macropores, pore diameter is greater than 50 nanometer. Right? So we all know, right? So on the surface of a catalyst, we have got pores. First of all, you tell me one thing. Let's assume we are conducting one heterogeneous catalytic reaction. Heterogeneous catalytic reaction means you have got reactant, product in a different state, and catalyst in a different state. Let's assume I have got a gas phase reaction means taking place in the presence of a solid catalyst. So this will come under the heterogeneous catalysis, since reactant products and the catalyst are in the different phase here. Okay, maybe the reactant is in the gaseous form, product is also in the gaseous state. However, the reactant will be in the solid state. So this is all about the heterogeneous reaction. So Varun, tell me, when we carry out one heterogeneous catalytic reaction from A to B, so how many mechanistic steps are there?
Well, I think first is adsorption,
First of
and
all, tell
then
me the number, then start answering. First of all, tell me how many steps are there.
four.
No. There are 7 different steps involved. Let's assume I have got a simple heterogeneous catalytic reaction, A giving B. Right? So the reaction is conducted in the presence of a porous catalyst. I told you, right? So porous catalyst. So I mentioned what are the different kinds of pores one catalyst surface might possess. Okay. So first of all, what will happen is there will be diffusion of A from the bulk phase to the external surface of the catalyst. Right? So from the external, next step would be from the external surface of the catalyst, there will be diffusion of gas molecules to the pore mouth. This is step number 2. Step number 3 would be what? Adsorption of the gaseous reactant inside the active surface sites of the catalyst, active surface sites residing inside the pores. This is step number 3. Step number 4 is reaction will take place. Okay. Step number 5 is desorption of the product. Step number 6 is desorption of the product from the pore mouth to the external surface sites, right, of the catalyst. And step number 7 would be diffusion of the product from the external surface of the catalyst to the bulk phase. Okay, so there are seven different steps involved in such reaction. So we are conducting one gas phase reaction in the presence of a porous catalyst. Let's assume the reaction is A giving B. Okay, so first of all, from the bulk phase, the reactant gas will diffuse from the bulk phase to the external surface of the catalyst. The next step would be diffusion from the external surface of the catalyst to the pore mouth of the catalyst. Pore mouth means there are different types of pores available on the surface of the catalyst. Third one would be adsorption of the gas molecules, that means the reactant gas molecules I'm talking about, inside the pore mouth. Okay, inside the pores means inside the pores we have got active surface sites. So most of the heterogeneous catalytic reaction take place inside the pore mouth. Okay, so inside the pore mouth there are active surface sites. So inside active surface sites we have got first of all adsorption of the diffusing gas molecules. So followed by adsorption, what will be there? So there will be reaction. So reaction will be taking place. So reaction will produce certain amount of products. So what will happen is desorption of product will take place. So next would be the diffusion of the product from the pore mouth to the external surface of the porous catalyst. This is step number 6. What would be our step number 7? Step number 7 is diffusion of gas molecules or the product molecules from the external surface of the porous catalyst to the bulk phase. So these are the seven different steps involved in such heterogeneous catalytic reaction. Always remember this. Okay. So with this understanding, I'll move to the sintering. Sintering can be of two types. Okay, so aggregation, you talked about the aggregation, right? Aggregation has got everything to do with the melting of the active metal part. Since melting can take place only in the active metal parts, why is it so? Since support, I already mentioned that the support material has got a high surface area. Not high surface area, high melting point. So if it is above 1000 degrees Celsius, so there is a minimal possibility of the aggregation for the support material, right? So I told you, means there are several characteristic features I mentioned about the support, that the support should have medium to high surface area, it should have high melting point. So melting point should be above 1000 degrees Celsius. So that's why we're using silica, silica alumina, alumina silica, okay, alumina, zeolite, sometimes molecular sieve also, since they have got high melting point. So if it has got high melting point, so melting of the active metal will only take place. Okay, since most of the reactions we carry out below 1000 degrees Celsius in a petroleum refinery or in some other industries. So this is called the sintering operation. Okay, so formation of aggregation of particles, I'll talk about it now. Before that, narrowing of the pores. Let's go one by one. So there are two possibilities of sintering. One is narrowing of the pores, and the second one is the formation of the aggregation of particles. So first of all, let's talk about the narrowing of pore. Let's assume I'm carrying out one gas phase reaction at a temperature of around 800 degrees Celsius for a longer period of time. Okay, so again, this is our catalyst. Okay, so this catalyst means we have got like active metals, and this is our support. So these are not the active metals. Here I don't want to show you the active metals since I'm handling the pores. Narrowing of the pores I'm talking about. So I'll show you the pores. Let's assume I have got this kind of pores with dimension 2 nanometers. Okay. So if we are carrying out the reaction at a temperature of around 800 degrees Celsius, let's assume we are carrying out the reaction for several days now. So what will happen is there will be narrowing of the pores, right? So pores will get narrower with time at a high temperature. Okay, so let's assume previously we started with 2 nanometers pore diameter, and here the pore diameter has reduced to 0.5 nanometers. Try to understand this. Okay, so from 2 nanometer to 0.5 nanometer. So what was the main reason behind this transformation? The main reason is we are carrying out the reaction at 800 degrees Celsius and for several days. Okay, so what will happen is, and remember, whenever in petroleum refinery or in some other industries, whenever we carry out any gas phase reaction, this is a continuous mode, right? And we always want the reaction to be continued for at least 1 to 2 years without any sort of interruption. Okay, so from 2 nanometers, it has reduced to 0.5 nanometers or even lesser than that. But the gas molecule has got certain size, and the size of the gas molecule remains unchanged. Try to understand this. So when we have got pore diameter like this, 2 nanometers, let's assume the catalyst, not catalyst, the reactant gas molecules has got a like size less than 2 nanometers. So what will happen is easily they can go inside, go and get inside this pores, right? And the diffusion of gas molecule won't be that difficult since they have got size around some Armstrong. Let's assume is 10 Armstrong. Okay, 10 Armstrong means 1 nanometer. So there will be diffusion, enough diffusion of the gas molecules inside these pores, and simultaneously you can carry out the reaction. But what will happen is when the pores gets narrower, let's assume 0.5 nanometers, but the gas means size of the gas molecule remains unchanged, like 1 nanometer, and here the pore diameter has shrunk to or reduces to 0.5 nanometers. So 1 diameter means 1 nanometer particle size means gas molecules cannot penetrate through this, right? Due to the diffusion limitation. Why diffusion limitation? The size of the means reactant molecule is greater than the pores. If the size of the gas molecule is greater than the pore size, then what will happen? Gas molecule will not be able to come in contact with the pores. Okay, they will always hit the pore mouth and they will repel back. They won't be able to penetrate through those pores. Right? Is it justified or not? Tell me.
Yes, sir.
Initially, we started the reaction at 800 degree. We have got certain pores, like means catalyst has got certain pores. Here the pore diameter is around 2 nanometers, and we are allowing the gas molecules to pass through it. So gas molecules will do what? The gas molecules will come in contact with the pore mouth, and it will again follow the 7 steps that I mentioned just a few minutes back. So these gas molecules will come in contact with the pore mouth and they will diffuse inside this pore mouth and they will be captured by the active surface sites and the reaction will take place. And here the gas molecule size is around 10 Armstrong. Okay, so the size of the gas molecule remain unchanged during this process. Okay, so if I am purging like hydrocarbon gas molecules, let's assume carbon dioxide gas. So carbon dioxide gas molecule has got certain size, right? So this will remain unchanged. This will be irrespective of the temperature or other reaction conditions. Okay, size of the carbon dioxide gas molecule won't change. However, what will change is the pore size inside the catalyst will change. Here the pore size has reduced to 0.5 nanometers. However, the size of the carbon dioxide gas molecule is 1 nanometer. So what will happen is this carbon dioxide gas molecule, the moment it will come in contact with these pores, they won't be able to penetrate through those pores due to the diffusion limitation. What is causing the diffusion limitation here? The restriction, size restriction. What is the size restriction? The gas molecule or the reactant molecules has got the high means has a greater size or the has got the dimension greater than this dimension. This is 1 nanometer and this is 0.5 nanometer. Okay, so simply because of this, what will happen is we have got less productivity. That means if the gas molecule doesn't come in contact with the active surface sites residing inside this pores, then there will be no reaction as such. There might be some reactions on the external surface sites also, since the external surface of the catalyst also has got certain active surface sites, but these are minimal, okay, in number. Okay, so they have got less number of active surface sites. So whatever active surface sites these gas molecules means get the external surface of the catalyst. So this will be responsible for the catalytic reaction. So what will happen is the overall productivity will decrease. Why is it so? Due to the size restrictions. Okay, and most of the part of the active surface sites will remain unchanged or remain unconverted or uninteracted rather. So as a result, the overall productivity will decrease. So this is all about the narrowing of the pores. So when we have got narrowing of the pores, so how to get rid of narrowing of the pores, I'll talk about this later. Okay, so for the time being, remember narrowing of the pore means the pore diameter of the catalyst particles or pellets reduces if we carry out a reaction at a high temperature for a considerable period of time without any interruption. Okay, so then this type of situation will arise. So this is called the narrowing of pores. Okay, so this is means very important. This is a very important thing in a refinery or in some other industries also where we carry out a reaction at a very high temperature. Okay, so this is narrowing of pores. And the second one is the aggregation of active metal particles. So Varun has already talked about this thing. This has got everything to do with the melting point. Always remember that when we carry out a reaction at a high temperature, then melting of the active metal will take place. However, there will be no melting of the support material will take place. Why is it so? Since support material has got high melting point above 1000 degrees Celsius. But in most of the reactions, we will carry out the reaction much below means 1000 degrees Celsius. So there is every possibility that the aggregation will be due to the melting of the active metal particles. Okay, so let's assume we have got this is basically the pictorial representation of a supported catalyst. I have already talked about these things and this image you have seen before also, right? So this is a pictorial representation of a support material, and on the surface of a support material we have got uniform and homogeneous distribution of the active metals. So these spheres are basically the active metals. Remember, we are carrying out the reaction at high temperature for a longer period of time. Okay, so what will happen is, as the time will progress, what will happen? These particles will come closer to each other. That means these are the adjacent particles, right? So these adjacent active metals will come in contact with each other, and at one time will reach, then they will come in contact with each other in this fashion. Okay, there will be no gap between two adjacent particles. Here they are equal spaced, not equal spaced, but we assume they are equal spaced. Since we cannot calculate and means enter each and every particle like this. Okay, we don't have any control over these things. Okay, they are not equal spaced, but we assume that they have got enough space in between them. But here, if we are carrying out the reaction at high temperature for a longer period of time, then we'll end up with this kind of situation. That means the adjacent particles are in the close proximity. Okay, so why is it so? So this is the intermediate condition. And what would be our final condition? So final condition will be like this. So is this understandable to all of you? Like, first of all, initially we started with this. We assume that all the particles or the active metal particles are equally spaced, okay, or evenly distributed. But as the time progresses and we are carrying out this reaction at a temperature, very high temperature, let's assume at around 750 or 800 degrees Celsius. So this condition will arise. So this is means two adjacent particles will come in close contact with each other. They are in close proximity, right? So this is the intermediate state. So what would be our final state? Our final state will look like this. Okay, so this is all due to the melting of the active metal particles. So melting, due to the owing to the melting operation, we ended up with this kind of configuration. Okay, so when we have got this type of situation, first of all, let me talk about this situation. When we have got this situation, so all the active sites of this particle or this active metal is available for the gas molecules to penetrate or come in contact with, isn't it? So diffusion of gas molecule can take place from here, from here, from here, from here, from everywhere. The same is applicable to this particle as well, and so on. Okay. So this is the initial condition. Here what will happen is we have got minimal surface area, active surface area available for the diffusion of the gas molecules, isn't it? Since this part is not available, this part is not available, this part is also not available, etc., etc. And same will be applicable for these three particles as well. Only this part is available, the top part here and from this side. Okay, so the gas molecule can come in contact with the active metal part. But when this kind of situation will arise, then what will happen? Only the top surface and the edges are available for the reaction. This measure means most of the part of the catalyst particles will be like not available for the reaction, since it will be very difficult for the gas molecules to penetrate through this part to this part. It won't be, gas molecule won't be able to come in contact with this part. Look at the image, then it will be understandable to all of you. So only the diffusion of gas molecules, or the gas molecules will come in contact with the active particles over here, over this part, means top surface, and two edges. Like these two edges are available for the reaction. However, most of the part of inside this active metal part will be unaffected, okay, or will not take part in the reaction, since this part will be not accessible. If something is not accessible, then how would these molecules, gas molecules, will come in contact with them? They won't be able to come in contact with them, right? So as a result, the overall productivity will decrease. Okay, so always remember this kind of pictorial representation or schematic representation. If you remember this, you don't have to memorize anything. So initially we started with this, they are equally spaced particles, adjacent, but as the time progresses, the adjacent particles will come in contact with each other. And that means the space between two adjacent particles will decrease with time, and one time will reach when this kind of configuration will we will end up with this kind of configuration. So when we have got this kind of configuration, then what will happen is most of the part of the active metal will remain unaffected during the reaction. Why is it so? Since because of the diffusion limitation, this part of the active metal, okay, will be unavailable for the reaction to take place. Okay, so as a result, the overall productivity will decrease. So in order to avoid such situation, what one should do is will carry out the reaction at a temperature that is around 0.3 to 0.4 times lesser than the melting point of the catalyst. By catalyst means I am talking about the active metal part. Okay, in order to avoid such situation, what we need to do is, let's assume my metal has got like active metal like copper, or let's assume I have got silver. Okay, so we don't want to achieve this situation. So in order to avoid this situation, we need to carry out the melting point. Let's assume melting point of silver is around 500 or 600 degrees Celsius. So 0.3 to 0.4 times lesser temperature we will be using as a reaction temperature. Okay, in order to avoid such situation. But remember, when we have got this kind of situation, we cannot carry out the reaction any further. We'll have to terminate the reaction, and we'll again have to regenerate the bed. Means here regeneration will be quite difficult, and we have to replace the catalyst particles in such case. Okay, if we have got coke deposition, then we can do like this. We can do regeneration using various techniques. However, there are two different methods available for the regeneration of the catalyst when we have got coke deposition issue. But whenever we have got aggregation issue, it is next to impossible. It is very difficult to regain this kind of configuration from this. So if you have got this kind of configuration from this to this, it is highly unlikely. Okay, so we can't do this. So better what we do is we throw this off and we take a new bed of catalyst. Okay, but this is expensive. Okay, so in order to avoid such situation, what we do is we need to carry out the reaction 0.3 to 0.4 times lesser than the melting point of the catalyst. Okay, so you take some break. I need to drink some water. My voice is getting choked. So we'll reassemble again in 5 more minutes. In 5 minutes, okay? Okay, so is this clear to all of you, or should I repeat again? Shall I repeat, or this part is okay with everyone?
This is clear.
This is clear, right? Remember, in the exam, I'll ask conceptual questions from here. Okay. So, sintering part is over. So sintering has got, like, sintering can be means occur. Sintering can occur by two different ways. One is narrowing of pores, and the second one is formation of aggregation of the active metal particles. Okay. So in order to avoid sintering, we need to carry out the reaction 0.3 to 0.4 times lesser than the melting point of the active metals. Okay. So since we don't want to arise this situation, we don't want to encounter this situation. Okay. So the third one is the called the poisoning. So what is poisoning? So tell me, what is poisoning? I already told you that the impurity, if you have got impurity in the feedstock, then poisoning can happen. So what is poisoning? Give one example and tell me. What is poisoning? Yes.
Loss of catalytic activity due to presence of a trace metal or compound in the feed, basically. It permanently bonds with the catalyst and reduces its effectivity,
Right.
like its efficiency.
Right. Right. So poisoning, by the way, tell me, what are the different sulfur containing impurities we can have? I have already talked about these things in the class. While teaching you the thionation reaction, if you remember, I talked about this, right? So what are the sulfur containing impurities? Take name of two names. Take name of two sulfur containing compounds.
So mercaptan could be one.
Mercaptan is one, and what else?
Uh, can hydrogen sulfide also be considered?
Hydrogen sulfide is the product.
Oh yes, sir.
It's when we have got sulfur containing impurities. So hydrogen sulfide is the product. We carry out one reaction in today's class. I'll talk about that reaction. Okay, so that reaction is called the hydrodesulfurization method. So what we do is, at very high pressure of hydrogen, we carry out the reaction, and as a result, sulfur containing compound comes in contact with hydrogen, producing H2S. So H2S is the main product. So sulfur containing impurities are removed in the form of H2S. So H2S is not the sulfur containing impurity here. Okay, sulfur containing impurity can be either mercaptan, thiophene also. Thiophene is the major impurity present in the feedstock for petroleum refinery. Okay, always remember this. So let's talk about the poisoning. Poisoning means when we have got a feedstock. So try to think of the normal situation. So we have got a reactor system. We have got certain feed that is entering and flowing through that reactor, and as a result, from the outlet, we are getting certain products. So this is the real situation, right? So this is our overall goal. So when our feedstock is not pure, so it is always desirable to feed means to have a feed which is highly pure in nature. That means it is 99.99% pure feedstock has to be charged inside a reactor system. So this is the standard protocol. But in some cases, what people generally do is means they don't care about these things. So whatever impure feedstock they obtain from various industries, they, without any sort of pre-treatment, okay, they feed this feedstock into the reactor system, and then what happens? Then poisoning happens. So when our feedstock is rich in different impurities like arsenic, sulfur, chlorine, and so on, okay, then we can see the poisoning effect. So poisoning effect means irreversible chemization of the poisoning particles with the active catalyst surface sites or active metal surface sites. Okay, so here our feedstock, without any pre-treatment, we're allowing the feedstock to come in contact with the bed, okay, made up of the catalyst pellets. Remember, here catalyst pellets having like diameter roughly 3 nanometers. Not nanometers, sorry, this is 3 millimeters. Okay, so 3 millimeters diameter catalyst pellets are there. And this is called the poisoning effect. So what will happen is we have got a feedstock, that feedstock enters, that flows through the bed, and whatever products we are getting, so this product is also impure, first of all, and secondly, the productivity will also decrease because of the poison of the catalyst. Okay, so here our feedstock is having poisons like arsenic, sulfur, and chlorine. Okay, so without pre-treatment, we are allowing the feed to come in contact with the reactor system, and we are getting certain products. The productivity will say automatically decrease owing to the like presence of this kind of impurities. Okay, so at the same time, what will happen is the catalyst poisoning will take place. Why is it called catalyst poisoning? Since these impurities will form a bond. Okay, this is a irreversible chemical bond formation between the poisoning particles and the active metal part of the catalyst. Okay, so this is called the poisoning effect. So we cannot, in order to avoid the poisoning effect, what we need to do is, first of all, whatever feedstock we obtain from various industries, that has to be passed through a pre-treater for the pre-treatment purpose, and the feedstock that comes out, that means the effluent that comes out from the pre-treater unit, that should be our main feedstock. Okay, not the raw feedstock that we obtain from various industries. So there has to be one filter in between whatever feedstock we obtain from the industry and whatever feedstock we are feeding to a reactor system. Okay, so there has to be one like filter. So what is kind of a filter? This is called the pre-treater. So we need to have a pre-treater. So the feedstock coming from various industries, first of all, this is passed through a pre-treater. Pre-treatment takes place. That means the removal of these impurities will take place, and the feedstock would be reaching, that feedstock that comes out from the effluent part of that pre-treater is called the is in the purest form. That means in the 99.99% purity we can obtain by passing the feedstock through a pre-treater. So now let's assume I have got a feedstock. That feedstock is 100% pure and allowing it to pass through this reactor system, and we are getting certain kind of product with desired yield. Okay, so this is our real life situation now. Let's assume I have got a feedstock like this. I have got a feedstock. These arrows represent the feedstock, and these are our like active metal part, and this is the support. Okay, so the feedstock is impure now. So we have got sulfur containing compounds, right? So these sulfur containing compounds will form a chemical bond with these active metals. So this is basically an irreversible reaction between both of them. So irreversible bond formation is taking place here. So this is chemisoption, means bond formation. Okay, so the bond formation is taking place here between the active metal part of the catalyst and the poisoning particles. Like here, I am considering sulfur as a poisoning element or particle. That's why the chemical bond formation is between the active metal and the sulfur. Okay, so this is the irreversible chemisoption of sulfur onto the catalyst surface sides. So consequently, the productivity will drop down. So everybody understands this. When we have got irreversible chemisoption, this is when catalyst poisoning has taken place. So most of the part of the active metal part is not active, not available for the reaction. That is why the productivity has dropped down. Okay, so first of all, what we need to do is the whatever feedstock we have, that has to be pre-treated. So now coming to the pre-treatment. So is that part clear to all of you? Here I have considered sulfur as a means poisoning particle. So if I consider say, arsenic as a means poisoning particle, so instead of sulfur here I will write AS, AS, AS. If I have got chlorine as a impurity, so chlorine will also have a poisoning effect. So chlorine will also form a irreversible bond with the active metal part. Okay, so irreversible bond formation is taking place over here. So this is all about the catalyst poisoning. Okay, so here deactivation kinetics and all, I'm not going into that. If means I'm allowed to teach you chemical reaction engineering, then I will talk about those things. But this is beyond the scope of this class. If I talk about those things, I won't be able to complete the syllabus. So means if you remember this, then this will be sufficient for you to understand what is catalyst poisoning. So catalyst poisoning means irreversible chemisoption or irreversible bond formation between sulfur, arsenic, chlorine with these active metals. Okay, so the productivity has dropped down due to the catalyst poisoning. So whatever feedstock we have, we are now going for the pre-treatment of the feedstock. So now let's talk about the sulfur containing impurities. Since sulfur is common to you now, we have already studied what is cyanation reaction. So sulfur containing impurity, we all know about this. So let's talk about sulfur containing impurities in the feedstock. Okay, so sulfur containing impurity we have got in the feedstock. So we need to carry out a reaction called hydrodesulfurization. So hydrodesulfurization reaction I'll be talking about when I will teach you the petroleum refinery. Since in petroleum refinery, I'll talk about different reactions like catalytic reforming, okay, hydrocracking. In those reactions, hydrodesulfurization reaction take place. Okay, so this removal of sulfur, these kind of reactions are considered to be the low reactions. There are certain high reactions and low reactions, right? While teaching you the paraffin dehydrocyclization reaction, if you remember, okay, so I told you that this reaction is considered to be the high reaction since this reaction produces aromatic compound. But what are the low reactions? Means removal of sulfur, oxygen, nitrogen containing impurities. They are treated as the low reactions. Okay. So now let's talk about the hydrodesulfurization, which is considered to be the low reaction since it is the removal of sulfur from the feedstock. Okay, so for hydrodesulfurization reaction, we carry out the reaction at a temperature of around 250 or 300 degrees Celsius. Okay, but in the petroleum refinery, we can carry out the reaction at high temperature as well, like at around 450 degrees Celsius as well. Okay, so this is the chemical formula of thiophene. By now, all of you know this. Okay, this is thiophene, like 4 carbon. This is, tell me, is this an aromatic compound? Is thiophene an aromatic compound? Yes. Is this an aromatic compound?
Yes, sir.
This is an aromatic compound. Why?
So I think according to that rule, I forgot the name, 4n plus 2 electron, and using S is
No,
the sulfur has a.
no, it is. It has got sulfur, but it cannot be treated as a like as an like aromatic compound. The simplest aromatic compound is benzene, right? 6 carbon ring with alternate double bond, single bond.
So I was thinking based on the electron rule.
No, from I understand what you are trying to say. Electron donor, those things also means in case of a like aromatic compound and as an in case of an aromatic compound, there has to be 6 carbon with three alternate double bond, single bond. Benzene is the simplest aromatic compound one can think of. Okay, these are all naphthenic compounds. These are all like cyclic compound, like cyclopentane, This is like cyclobutane kind of a compound. Okay, this has got naphthenic characteristics, but it doesn't have any aromatic characteristics. Aromatic, if it is considered to be an aromatic compound, then there has to be 4 carbon rings. 6 carbons. So benzene is the simplest aromatic compound we can think of. And means also there has to be at least 3 double bonds inside the ring structure. Here we have only 2, right? And also we have got only 4 carbon here. So this is not an aromatic compound. This may be considered to be an like naphthenic compound, but I'm not sure. Nobody tells this is a naphthenic compound either. Okay, but kind of a naphthenic compound we can think of. Okay, so this is the chemical formula of thiophene. It's a 4 carbon means compound. Okay, so this is C4H4S. This is the chemical formula of thiophene. So hydrodesulfurization means the reaction will be performed in the presence of hydrogen as a feedstock. Okay, so hydrogen plus thiophene. So at very high pressure, we are allowing hydrogen to interact with thiophene that produces H2S. Okay, so H2S has got several end applications as well. When I'll talk about the sulfur manufacturing, so oxidation and reduction of H2S is a very common technique to synthesize or to obtain the sulfur. Okay, so this whatever H2S we obtain from this reaction, this is transported to the sulfur manufacturing unit. Okay, so this is the reaction between thiophene and hydrogen producing H2S. H2S is our main product of this hydrodesulfurization reaction, and H2S can be transported to the other industries, especially to the sulfur manufacturing industries. Okay, so this was thiophene, and next I'll talk about another compound. This is also very much available in the feedstock from various industries. So this is RSH. RSH means alkyl mercaptan. Okay, so RSH that interacts with hydrogen producing H2S. Okay, RSH plus H2 giving H2S. This H2S also can be transported to the industry like sulfur manufacturing industry. So these two reactions are considered as hydrodesulfurization reaction. Okay, let's assume we have got chlorine containing impurities present in the feedstock. So how to get rid of this? Again, we'll allow H2 to interact with the chlorine containing compounds. Let's assume I have got a alkyl chloride. R is the alkyl group. Okay, so alkyl chloride is there. So alkyl chloride interacts with hydrogen producing RH rather. That means this is alkane plus HCl. So this reaction is conducted at high temperature, not a very high temperature, around 250, 300 degrees Celsius. So HCl will be in the vapor state. Okay, so this HCl will also be collected. So here I am talking about the removal of sulfur containing impurities and chlorine containing impurities. And let's assume I have got a arsenic compound present in our feedstock. Then how can we remove arsenic or chromium 6? Chromium 6 means hexavalent chromium. Okay. So when we have got like arsenic and hexavalent chromium containing impurities present in our feedstock, then how to get rid of this? Any idea? Any idea, guys? Yes. Let's assume I have got a feedstock. Okay. So this feedstock is rich in and means arsenic and chromium. So both of them can have poisoning effects. Arsenic has got poisoning effect. Even chromium also has got poisoning effects. So there is a method called adsorption, AD. Okay, not AB. Adsorption. We can carry out adsorption operation to get rid of arsenic and chromium 6 containing, that means hexavalent chromium containing compounds. Okay, so how can we do adsorption? For adsorption, we all know there has to be one adsorbent, right? So adsorbate, what is adsorbate and what is adsorbate? Adsorbate means the substance which is getting adsorbed onto the surface of a solid particle called adsorbent. Okay, so here for the removal of arsenic and chromium 6, we need to use iron or iron oxide deposited on activated carbon as an adsorbent. There are several research articles showing that the combination of iron or iron oxide and activated carbon can act as a beneficial can act as an effective adsorbent for the effective removal or efficient removal of arsenic and hexavalent chromium. Okay, so when we have got arsenic and chromium containing impurities present in our feedstock, we'll go for adsorption. So for adsorption, we need to have certain adsorbent, right? So adsorbent means we need to have a solid particles onto which means arsenic and hexavalent chromium will get adsorbed. Okay, so this is our main adsorbent. However, there are several different adsorbents can also be used. Okay, but research article shows that iron in the zero valence state or iron oxide in +3 oxidation state that is deposited onto activated carbon can act as a superior adsorption agent, or adsorbent can act as a superior adsorbent. So when we are handling sulfur and chlorine containing impurities, we'll go for hydrodesulfurization and hydrodechlorination methods. Remember this. However, when we have got arsenic, chromium containing impurities present in the feedstock, then we don't go for this. Then we go for a technique or several separate method called adsorption. So what is adsorption? to carry out the reaction, means carry out this removal process in the presence of a suitable adsorbent. So what could be our suitable adsorbent? Here either iron or iron oxide deposited on activated carbon acts as a suitable adsorbent in this case. Okay, so adsorption operation will be performed to remove arsenic and chromium 6 containing impurities. Okay, so I'll stop here since I won't have time to start the sulfur and sulfuric acid manufacture today. So on Monday, I will start from here. Okay, so whatever I have taught you today, means if you have got any doubts, any queries, you can just put forward right now. Yes, we'll stop the class for today. Any doubts? I have covered so many things today. So if you have got any doubts, please tell me now. Any doubts, guys? If no doubts, then we'll stop the class today here. Again, we'll reassemble on 20th, I suppose. Not 20th, 21st rather. Okay, so next Monday, see you. See you on next Monday. Thank you, guys.
Thank you, sir.